Hello, everyone, and welcome to today's lecture recap. So last time we were talking about a new subject, which was the subject of oscillations, and this is sort of a universal thing that happens anytime you have a system which is perturbed about some kind of a stable mechanical equilibrium situation. So let's kind of remember what is it that causes these sorts of oscillations that we talked about last time. And the idea is that these will arise very universally when you have a situation such as we have here, where now the system is in mechanical equilibrium, so the net forces are zero, but where you also have this condition that the equilibrium is stable, which means that if I displace in one direction, for example, by pulling downward on this duck mass system, then there's an upward restoring force that tends to bring the system back towards the equilibrium position. And similarly, if I displace in the other direction, so if I move our system here upwards above the equilibrium position, then if I let it go, then there's a downward restoring force. And so we understood that this leads to oscillations because if you say start in this position and let things go, then the upward restoring force will cause an upward acceleration of our system that increases the upward velocity. And then when we get back to the equilibrium position, we now have some upward velocity. And so we keep going above the equilibrium position. Now there's a downward restoring force, so a downward acceleration that slows our upward velocity and stops it, and then starts accelerating us, a downward velocity. And so now we move downward past the equilibrium position. And again, eventually we stop, but we have upward acceleration, and so it repeats. And so then overall, we end up getting this periodic kind of oscillation. And so then last class, we tried to understand the mathematical description of that. And we said that in general, whenever we have restoring forces, we could imagine making a plot, for example, of this restoring force versus displacement from the equilibrium position. And this can take many forms, but what we know in general is that it's going to be, for negative displacement, the restoring force will be positive. For positive displacement, the restoring force will be negative. And so if you zoom in to the region where you're talking about very small displacements, so starting from equilibrium, if I just move up a tiny bit or down a tiny bit, then the form of that function is going to look linear in almost all situations. And so we can model that, the form of the restoring force, the net force on the object, versus the displacement from the equilibrium position. That's going to look like a line. It's going to have a negative slope, and we'll just call that slope k. So k is determined by the properties of the physical system that you're studying. In the case of this spring system, it's just what we call the spring constant. So you've seen that equation probably in high school in describing what's called an ideal spring. It's supposed to apply for all displacements of an ideal spring. For a realistic spring, or for other kinds of systems such as the piston in a cylinder of gas that we studied last time, then this equation is going to hold as long as x is small enough away from the equilibrium position. So it turns out that when we have a force which is of this form, then we can actually use Newton's laws to predict precisely what is the motion of our object with respect to time. And so the way to do it is start with Newton's second law. So that's acceleration is equal to F over m. That's a different way of writing it. But I'm writing this to emphasize the way that we can use this to kind of predict the future. Okay, so this A equals F over m, which in this case is minus K over mx. We think of that as an equation that tells us the rate of change of the velocity. Predicts how will the velocity change given, in this case, the initial position of our object. And then the definition of velocity itself will tell us how the position will change going forward. So it tells us the rate of change of position. And so if you look at the combination of these two equations, Newton's second law and then the definition of the velocity, what you see is that they predict the rate of change of position and velocity given the current position and velocity. So we can then, you can see that those should then determine the future motion. So if we know the position and velocity now, these equations tell us the rate of change. Then we could predict the position of the velocity a slight time into the future. Then we could use these equations again. And so there would be this iterative process that we could use to figure out the position and the velocity all of the times in the future. This is how you would, for example, program a computer to predict the motion of our object. Mathematically, we have tools of solving these equations directly using the methods of differential equations. Since not all of you are familiar with those methods, what we can do, what I'll do in this course is basically rely on your understanding then, as I explained, that these equations should predict the future motion of the system. And then I'll just tell you a solution that you can check satisfies the equations and allows any initial position and any initial velocity that might arise. Okay, so the claim is that if you solve these equations mathematically, that what you find is that the most general solution looks like a cosine function with some amplitude, some phase, and some parameter omega. This is the Greek letter omega, which is related to our spring constant and our mass in this way. So let me just actually go through the steps of how you would check this. So starting with position x of t equals a cos omega t plus phi, if we wanted to check that that function of time satisfies these equations, we basically first compute the velocity by taking a derivative of this function and using the chain rule that first gives us negative sine of omega t plus phi, and then we differentiate the inside, so that gives us another factor of omega outside. So once we have that velocity, then we can take another derivative to calculate the acceleration. That turns the sine back into a cos, gives us another factor of omega from the chain rule. And now we can check to see whether that is equal to what it's supposed to be equal to, which is minus k over mx. Okay, so this was our Newton's law equation that dv by dt was supposed to be equal to minus k over mx. We see from this function that it's equal to minus omega squared x. And so our equations will hold as long as we choose the right value for omega. So omega should be equal to k divided by m. But we're allowed to choose any value for a and any value for phi, and it still works. Okay, so here's our final solution then. If we have a system which has a mass m and it has a restoring force whose slope versus the position is minus k, then this is going to be the form of the motion. Okay, and so I've told you that the omega is determined by these properties of the system, the restoring force, slope, and the mass. And I said that this solves the equations for absolutely any value of a and phi. And so you might be wondering, well, what determines those? What determines a and what determines phi? So actually, I want you to think about that just for a minute. Maybe pause the video and try to think about, suppose that I take my physical system here. Maybe I pull down on the weight and then let it go. Okay, and now I want to imagine plotting the motion versus time. And so that should be described by a function like this. We've understood that omega should be determined by the spring that I'm using in the mass. But what determines A and phi? Okay, so let's talk about it. So the answer is that A, remember, is the amplitude of the motion. And so that clearly depends on what I do to set up the system originally. So I could figure out the amplitude by just looking at how far did I pull it down at the start. So that would be A, or how far did I lift it up at the start. So in those two ways of starting the motion, where we start at the top or the bottom, then the A would just be exactly how much did I displace it. In other situations, the A would be determined by looking at, so say another situation I could imagine starting this system off by would be to actually just give it some initial velocity. So if I just hit this, so then the initial situation is that I have a downward velocity, and then we'll understand this later. The A is going to be determined by how much initial velocity I give the system. So we'll do an example probably next class. What about the phase? Well, we'll talk about that again in this class in great detail later. But the phase has to do with where on the cosine function do I start. So if I plug in t equals 0, then my equation says x of t equals a times cos of phi. And so adding or subtracting a phase, we'll see that shifts the cosine graph to the left or to the right. And so depending on whether I started at the bottom, or whether I started at the top, or whether I started in the middle with some initial velocity, those different choices are going to be modeled by making different choices for the phase here. Okay. So I wanted to do a little bit of a demo, again, using this system with the duck. And so the way that I'm going to do it is to so what I want to do is actually show you directly that this up and down motion of the duck actually corresponds, if you plotted that vertical position versus time, to something that looks like a sinusoidal function. So that's not totally obvious just by looking at it what the shape of that function versus time is. And so in order to demonstrate that, I have a little video that we can watch here. Let's pause that. So what's going on here is that we've basically got some computer vision software that I set up, which recognizes the location of the duck. And so as a function of time, what the software does is basically puts a big red dot on the location of the duck. And then as time goes on, that dot moves to the left at a constant rate. And so in the video, what we saw so far was basically that you just get a horizontal line here. We can see that. And the horizontal line is basically because the vertical position is not changing with respect to time. So this is just the graph of height versus time when the height is not changing. Okay, so now let's run the video forward, and we'll see what happens as I displace the duck a little bit in the downward direction. And so now what you notice is, so as expected, the duck is oscillating up and down because we disturbed it from its mechanical equilibrium. And now effectively the software is just showing the history of the vertical position. And we see that it's a pretty nice sinusoidal curve here. So as the duck moves up and down, then the height as a function of time looks like a cosine. And so if we just pause that at a time, then we see that this is the history of the duck's vertical motion. And so one thing that's interesting is that the period here, it's going to be supposedly, according to our formulas, independent of the amplitude of our oscillation. Okay, so that period we'll see later in this class is directly related to the frequency of oscillation. And so if we now make a larger amplitude oscillation, so we let it move up and down more, okay, now it's wobbling around quite a bit. But if we let it settle down there a little bit, there we go. We see at least more or less the period or the frequency of that oscillation is pretty much the same as it was before for a small oscillation. And so that's an important property of simple harmonic motion. Okay. So that is pretty much what I wanted to say about the video. So let's head back. Okay, let's head back to our main screen here. I'll share the slides again. There we go. Okay, sorry about the initial silence there. Okay. And now we're back. Okay. You might have, okay, so let me just say the little story here. You might have been wondering, well, what's the deal with the duck? Why do I have a duck here? And it turns out that the reason is that I found some software, someone already on the internet had written this program in Python. There's a package for Python called OpenCV, which is a computer vision package. And I'm not some wizard Python programmer, but I just found someone else's program on the internet where they had made a program in Python to track the location of a tennis ball in an image. And so I thought, well, okay, I could use that. If I just find something yellow in my house, then it will track the location of that yellow thing. And I thought, well, tennis balls don't normally bob up and down, but maybe ducks, they generally bob up and down if they're sitting in the water. So I just happened to find this yellow duck. I have no idea where it came from. And so I put that onto the mass, and then bingo, we had a computer vision system that was able to track the vertical motion of the duck. And I just kind of changed the program a little bit to make it make that graph. So the moral of the story is there's lots of amazing stuff out there on the internet, and you don't have to generally do things yourself if you're trying to write some computer program. But of course, it's fun to understand how it all works and be able to do it yourself as well. Okay, so that's sort of our demo. What we want to do the rest of the class is basically walk through a few questions where we're going to understand how to figure out what these parameters are, either given a graph of the motion that we might make, or given some initial kind of experimental setup where I specify what the initial conditions for the motion would be. So the first thing I want to do is tell you how this parameter omega appearing in the cosine function is related to the period, which is much easier to measure physically. Okay, so the period is just the time between the top of the oscillation and then the next time the oscillation reaches the top. So that's easy to measure experimentally. How is it related to omega? So let's think about this question, which is the opposite. I'm going to give you a particular cosine function here. In this case, omega is equal to 3. And I want you to figure out what is the period of this cosine function. Okay, so take a minute to do that. Maybe pause the video, and then I will talk about it. Okay, so let's go through this. So we've got with our this is apparently primrose, the color of our crayon today. So x of t equals 5 cos of 3t plus 5. Okay, and so we want to know, like, what is the period of this function? And so we could do it in a couple of ways. The first one is to realize that this 5 isn't going to be very important. So that's just going to shift our function to the left or the right. It's not going to influence the period. This 5 just has to do with the height of our function. Again, that's not going to be important for the period. And so the main thing that will be important is this number 3. So the way to understand the period, I'll give you 2 methods. So one method is just to realize that if you have cosine of t, then the period is going to be 2 pi. And if you have cosine of 3t, so basically, in general, when you have a function and then you evaluate that function at say 3 times t instead of t, what this does, it just squishes your whole function into kind of a narrower, well, it just squishes the whole thing by a factor of 3. Okay, and the reason is you can see that if you have some value of t, and then here you just plug in 1/3 of that value, then you'll get the same result as before. Okay, so that just means that it's squishing everything along the x-axis here. And so that means if the period was previously 2 pi, then now the period is going to be 2 pi over 3. And so that would be our answer in this case. But let me give you another way to think about this. So just as an alternative, we could go back and look at this cosine function. Okay, and so we know it's some periodic function, and we want to know what the period is. And so another way to think about this is the period is basically what do I have to add to this little t in order for the function to come back to itself. And so, for example, with cosine t, we need to add 2 pi to t in order for the function to come back to itself. With cosine 3t plus 5, you notice that if I take t and I add to it 2 pi over 3, well, then the inside of the cosine goes back to, so this thing here, as I make that substitution, it just adds on 2 pi to what we had before, and so the cosine goes back to itself. Okay, and so we see that the period is, again, through that method, 2 pi over 3. Okay, this is the smallest thing I could add to the time in order for that to happen. All right, so either one of those methods would be fine to help you understand that the period is 2 pi over 3. So we could do that more generally. What we did was for omega equals 3, we understood that the period is 2 pi over 3. But the same argument would then tell you that if I had some other number there in front of the cosine, that the period is going to be 2 pi over that other number. And generally, we call this number omega. The jargon that we use is that that's the angular frequency. And so the period is 2 pi divided by the angular frequency. There's another version of frequency that is more commonly used in everyday life, which is just the inverse of the period. So the regular frequency is what we call f. That's just the oscillations per time. And we see that this is very simply related to the angular frequency. So the f is equal to 1 over t, omega equals 2 pi over t, and so omega equals 2 pi times the regular frequency. Okay, so in general, when we're going back and forth between frequency and these cosine functions, then probably you'll just be remembering or using this relation that the period and the frequency are related by t equals 2 pi over omega. Okay. So you have to be a little bit careful about what we're asking. Sometimes we'd be asking about angular frequency. Sometimes we'd be asking about regular frequency, but those are just proportional to each other. Okay, so let's now understand better the other factor here, the phase appearing in the cosine. And so I want you to take a moment to consider this question. The graph shows the displacement of some object. So in this case, it starts out at the maximum, But what about when I add a phase phi? So suppose that phi is some small positive number. What does that do to our function? Okay, so hopefully you've had a chance to think about that on your own. Let's start with the original function that I've drawn there. And so this is a times cos omega t. And now I want to understand what happens when I take a times cos omega t plus phi. And so what we realize is that this is something that it's going to shift our function to the left or to the right. It won't affect the height of the function. That's the amplitude A. It's not going to affect the frequency or period. It's basically equivalent. So adding this phi here is like replacing t with, so I could, if I replace t in this original function with t plus phi over omega, then we get the lower function. So it's some kind of a shift in the time, which is the x-axis in this case. And so what we need to understand is adding a small positive. So for phi positive, does that shift it to the right or the left? So here's how I think about it. Let's think of putting in t equals 0. Okay, then what we end up with is a times cos of phi. And so with the new function at time equals 0, what you're seeing is the old function at some positive time. Okay, so instead of seeing cos of 0, what we're seeing in the new function is cos of some small positive thing. Okay, and so if I were to plot the new function, that means at time equals 0, instead of this value, I'm seeing this value, which is already where the function is starting to come down. Okay, so you're looking into the future by adding the positive phase there. You're looking into the future a little bit, seeing the function where instead of at time equals 0, where it will be at a slightly later time. Okay, and so that means that a positive phase, so we see that what's happened by adding the positive phase, we've shifted our function to the left by a certain amount. Okay, so that shifts the graph to the left. And then the main thing we want to understand is, well, how much does it shift it to the left? Okay, so similarly, if we had a negative phase, that's going to shift it to the right. Okay, so a positive phase, you're seeing slightly into the future, and so that's like shifting the graph to the left. A negative phase, you're seeing slightly into the past. It's like shifting it to the right. And the way to understand exactly what the number phi is to realize that if we had a shift of an entire period, that would be phi equals 2 pi. Okay, so adding 2 pi inside, that would shift it an entire period to the left. Of course, it would just come back to the same function. But this is a useful way of thinking about it when we want to understand, say, a situation like this one. Okay, so here's a situation where we've got something that, well, instead of a cosine, it's a sine. And so we would say, okay, here's the cosine function. Our function looks like, I'll just plot it down here. Our function looks like this instead. Okay. And so what's happened is that we've shifted to the right. And so phi should be negative. But how negative is it? And so we see that our shift to the right is 1/4 of a period. So if it's a quarter of a period shift, then phi, or the absolute value of phi, is 1/4 of 2 pi. Okay, and so we conclude that phi is, so we said it was negative, and its magnitude is 1/4 of 2 pi, and so that would be minus pi over 2. Okay. Okay, so that's the answer for that one. Okay, and so just then in general, this is a good way to figure out what phi is. Okay, so you just look at your sinusoidal function, you look at how much is it shifted relative to the original cosine, and then you look at how much of a period is that shift. So you just take the fraction. In our example, it was a quarter period, but in general, you could take the shift divided by the period, and then you just multiply that thing by 2 pi, because an entire period shift would be a 2 pi phase shift. Okay. Then depending on whether it's to the left or to the right, use the positive sign or the negative sign. So that's it for today. We're going to do more examples next time, understanding these sinusoidal functions, how they relate to the graphs, and how they relate to the actual motion. But other than that, have a good weekend, and we'll see you on Monday.